All right, welcome to the deep dive. Today, we're going deep, really deep, into something that at first glance might seem like it's all about circuits and code, but it's actually grappling with some seriously big philosophical questions. We're talking about the philosophy of computer science.
Yeah, think of it as like a journey into the fundamental ideas behind what computation is, what software and hardware actually, all that stuff.
And you, our listener, you're a philosopher. You're already comfortable with these complex, abstract ideas, this deep dive. It's going to connect those skills, those ways of thinking to the digital world that we live in, the one that's all around us.
Exactly. And our guide on this journey, well, it's the Philosophy of Computer Science entry in the Stanford Encyclopedia of Philosophy. It's a super comprehensive, academically rigorous overview.
So what's our mission? What are we trying to do in this deep dive?
We're going to distill the core issues, the ontological questions, the what is it questions, and the methodological questions, the how do we know it questions in a way that speaks to that philosophical mindset.
Right on. So philosophers, we love definitions, right? Where does the philosophy of computer science even begin in defining what it's talking about?
Well, it starts with a big one. What is a computational system? And, it turns out there's not just one simple answer. There are a couple of main ways to approach this.
Okay, I'm intrigued. Let's hear them.
So one approach focuses on the relationship between software and hardware. It kind of treats them as separate types of things.
Okay, that makes sense. Software, that's like the algorithms, the code, the programs.
Yeah.
Hardware, that's the physical stuff like the chips, the hard drives, the actual machines.
Yeah, you got it. Software is often seen as abstract, existing in this realm of logic and information. Hardware, on the other hand, is concrete. It's tangible.
That seems pretty straightforward, like an everyday distinction.
Yeah.
But I have a feeling it's not that simple, is it?
You're right, it's not. For example, Moore, he argues that the software-hardware distinction, it's more like a convenient way to talk about these systems, not some fundamental difference in what they are in their being.
Oh, okay. So not an ontological distinction in philosophical terms.
Precisely. He emphasizes that no program just exists as a pure idea. It always needs some physical form, whether it's stored on a hard drive or, back in the day, even written on paper.
So the line between software and hardware can get blurry, depending on how you're looking at it.
Totally. What a programmer sees as software, an electrical engineer might see as a specific configuration of hardware.
This is where it gets really interesting. Suber, he takes this even further. He says hardware is actually a kind of software.
Yeah, he makes this bold claim. Suber, he defines software really broadly as any pattern that can be read and executed.
Okay, hold on. So any pattern, like my coffee cup, with its specific arrangement of atoms, could be software.
Well, in Suber's framework, yeah, because it has a physical structure. He argues that you could, theoretically, come up with a way to read and interpret that structure like a program.
Mind blown. So Suber, he's kind of blurring the lines, making hardware a subset of software. Then we have Colburn. He comes in with a slightly different take.
Right. Colburn, he sees software as this concrete abstraction, which sounds kind of paradoxical, but it captures something important.
Concrete abstraction, I like that.
Yeah.
How can something be both concrete and abstract?
Colburn, he argues that software always needs two things. A way to describe it, which is the programming language, and a way to execute it, which is the hardware.
Okay, so the software exists as this abstract idea, this code, but it needs a physical machine to actually do anything.
Exactly. And Colburn, he talks about this enlargement of content in computational abstraction. He means that as you abstract away from the physical details, you actually gain functionality. You make the software more powerful, not less.
That's interesting. It's different from, say, mathematical abstraction, where you might simplify to get to a pure form. In computer science, the abstraction adds layers of possibility.
Yeah, that's a good point. Then we have Ermac, who challenges this whole idea of software being both concrete and abstract. He's not buying it.
Oh, really? What's his argument?
He starts by saying abstract things lack both spatial and temporal properties, while concrete things have both. Software, he says, it definitely exists in time. It's created, it can be destroyed when all copies are gone. It's an artifact. But, he says, it doesn't have spatial properties. You can't point to it in space.
Okay, that's interesting. So software exists in the flow of time, but not in any particular place. That's a subtle distinction.
Right. So Ermac calls software an abstract artifact. It's temporal, but not spatial. And that's how he distinguishes it from pure mathematical abstractions, which don't even exist in time, in his view.
All right, so we've got Suber blurring the lines, Colburn with his concrete abstraction, and Ermac with his abstract artifact. And then Duncan comes along and says, Hold on, we need an even finer grained ontology here.
Yeah, Duncan's all about precision. He draws on this idea from Turner, the concept of a specification.
A specification like a blueprint that defines what the system should do.
Exactly. Duncan says a program acts as a specification for the machine. It tells the machine what to do, how to behave. If the machine doesn't follow the program, it malfunctions.
Okay, so the program is like a set of rules, and the hardware tries to follow those rules.
Right, and Duncan defines hardware as the artifact whose function is to carry out those computations to execute the software.
So, in his view, software defines what should happen, and hardware is what makes it happen, or tries to at least.
Precisely. So you can see this whole question of the software-hardware relationship, it's a rich area for philosophical debate.
It definitely is. Now, recognizing this complexity, the S entry introduces another way to think about computational systems. The idea of levels of abstraction, or low-A.
Yeah, this is a different way to slice the pie, so to speak. Instead of focusing on software versus hardware, it looks at how computational systems are organized into these layers, these levels of abstraction.
Okay, so levels of abstraction. We hear this term a lot. How does this perspective help us understand what a computational system is?
Well, it sees a computational system as a hierarchy. It starts with the most basic physical level, the hardware, and then it moves up through more and more complex design elements.
So like building blocks, each a level, relying on the one below it, but also hiding its complexities.
Exactly. Abstraction, it's a fundamental tool in computer science. It lets us manage complexity by focusing on the essential features while ignoring the low-level details.
Okay, I get that. We use abstraction all the time in everyday life to simplify things. But in computer science, it seems like it's more than just simplification.
Right. It's about creating new levels of meaning and functionality. For example, when you give a name to a reusable chunk of code, that's procedural abstraction.
Right, so you're creating a higher level concept that represents a whole bunch of lower level instructions.
Exactly. And it's important to note that unlike in some mathematical abstractions, in computational abstraction, the details aren't really gone. They're just handled at a lower level.
So the information is hidden, not destroyed. It's still there, being managed by those lower levels.
Precisely. Colburn and Shute, they emphasize this distinction. There's always an implementation trace, a connection to the concrete realization at a lower level.
All right, so computational abstraction, it's about building up layers of complexity and functionality, but those layers are always grounded in the physical reality of the machine. Now, our source lays out a specific hierarchy of these low A's for digital computational systems. What are the main levels?
Okay, so Primero, he outlines these levels starting from the top. Intention, specification, algorithm, high-level programming language instructions, assembly machine code operations, and finally, execution.
Okay, that's a lot to unpack. Let's start at the top. Intention, that sounds pretty philosophical. What does that even mean in this context?
Yeah, it's getting into the mind of the designer, the user. Intention, it's the initial cognitive act. It's what problem you want to solve, what goal you want to achieve.
It's the why behind the system.
Exactly. Like, let's say you want to create an app that filters out spam calls on your phone. That initial desire, that's the intention. It's not about the how yet, just the what you want to accomplish.
Right, so it connects to philosophical discussions about intentionality, goals, desires.
Yeah, definitely. And then comes specification, which starts to make that intention more concrete, more actionable.
So the specification lays out the specific requirements, the functionalities the system needs to have.
Exactly. It says what the system should do. So in our spam call app example, the specification might say it needs to maintain a list of spam numbers, check incoming calls against that list, and then block the spam calls.
Got it. Specification defines the what in detail. What's next?
Next is the algorithm. This is where we get into the how. The algorithm, it's the step-by-step procedure, the set of rules for actually solving the problem, for achieving those functionalities laid out in the specification.
Okay, so the specification says what to do, the algorithm says how to do it, and then we move from this abstract level to the more concrete level of high-level programming language instructions. This is where we get into actual code, right?
You got it. This is where programmers write the source code, using languages like Python or Java. These languages, They're designed to be understandable by humans, but they can't be directly executed by the machine.
Right, they need to be translated. And that's where assembly machine code operations come in, right?
Exactly. Compilers and assemblers, they do this translation. They take the high-level code and turn it into these low-level instructions that the processor can understand.
Okay, so we've gone from this high-level intention down through the specification and the algorithm to the actual code, and then finally that code gets translated into these machine-level instructions. And then what?
Then comes execution. This is where the rubber meets the road, so to speak. The physical machine, the hardware, it actually runs the machine code, carrying out the computations.
So according to this levels of abstraction view, a computational system is the whole shebang, from that initial intention all the way down to the physical execution.
Precisely. Each level, it has a meaning, a purpose, and it has a realization at the level below it.
Okay, that's a really powerful way to think about it. It's not just about software or hardware in isolation. It's about the whole interconnected hierarchy. Now, moving on, the SAPI entry digs deeper into the relationship between intention and specification.
Yeah, this is where we start to get into some really interesting philosophical questions.
So we have the initial intention, the goal of the designer or the user, and then we have the specification, which lays out the requirements. But getting from that initial, often vague intention to a precise set of technical requirements, that's not always easy, is it?
Not at all. It's a process of translation of interpretation.
You have to capture the essence of that intention, the what, and turn it into a detailed how.
Right. And Turner, he points out this crucial difference between models and specifications. Models, they're descriptive. They try to represent something that exists or might exist.
Like a model airplane represents a real airplane.
Exactly. And if the model doesn't match reality, you change the model. But specifications, they're different. They're prescriptive. They say how something should be built.
So if the system doesn't match the specification, you change the system.
Right. Turner, he says specifications have this correctness jurisdiction over the artifact, whether it's software or hardware.
So the system is correct if it follows the specification, and it malfunctions if it doesn't.
Precisely. But here's the thing. Specifications themselves can change. If they're too difficult to implement or too expensive, or if they don't actually capture the original intention, they can be revised.
So it's not a one-way street from intention to specification to system. There's this feedback loop, this ongoing process of refinement. And that brings us to what the SF entry calls the broader correctness problem, which is about more than just the final system meeting the initial specifications.
Right. Correctness, in the philosophy of computer science, it's not just about the end product. It's a concern at every level of abstraction, from the initial intention all the way down to the execution of the code.
Okay, I see. Correctness is a multifaceted issue. Now, the SP entry then connects these ideas of specifications and functions by talking about computational systems as technical artifacts.
Right, just like a hammer or a telescope. Computational systems, they're human-made things designed for specific purposes.
So they have both functional properties, what they're supposed to do, and structural properties, how they're built.
Exactly. And just like a screwdriver can be made of different materials, the same function in a computational system can be realized through different structures at different levels of abstraction.
Right. So you can have different specifications for the same intention, different algorithms for the same specification, different programs for the same algorithm, and so on.
Precisely. And each level provides the correctness criteria for the level below it.
So it's this chain of functional structural relationships. But the tricky part is verifying the correctness of the specifications themselves with respect to those initial intentions.
Yeah, that's where things get tricky, philosophically speaking, because how do you even know if the specification truly captures what the designer or user had in mind?
Right. It's about getting into those mental states, those intentions, which is a whole other can of worms. And that leads to a more general question. How do artifacts, in general, come to have functions?
That's a big one. There are a few main theories. One is the causal theory, which says an artifact's function is determined by what it actually does, by its physical capacities.
Okay, so a hammer's function is to hammer, because that's what it physically does.
Right. But this theory has trouble with things like malfunctioning. If a hammer breaks, does it stop having the function of hammering?
Right. And what about side effects? If you use a hammer to prop open a door, is that part of its function?
Exactly. Then there's the intentional theory, which says the function is determined by the intentions of the designer or the user.
So a hammer's function is to hammer, because that's what it was designed for. That's what people use it for.
Right. This theory can explain malfunctioning and side effects, but it raises its own questions.
Like, where does this intended function reside? Is it in the object itself or only in the mind of the person?
Yeah, that's a tricky one. And how do those mental states, those intentions, relate to the physical properties of the object?
Big questions. What about natural computational systems like, say, the brain? Do they fit into this framework of intended functions?
That's a good question. Some people argue that natural systems might not have explicitly intended functions in the same way human-made artifacts do, but they often exhibit what's called multiple specifiability.
What does that mean?
It means that the same physical structure or process can be seen as implementing different functions depending on how you interpret it. It depends on the labeling scheme, the perspective of the observer.
Okay, so the function isn't inherent in the physical thing itself. It depends on how an agent interprets it.
That's fascinating. Okay, we've covered a lot of ground on the nature of computational systems, the role of intentions and specifications, and this whole question of function. Let's shift gears now and talk about algorithms, another core concept in computer science.
Right. Algorithms, they're everywhere. We use them all the time, often without even realizing it.
But defining what an algorithm is precisely, that's surprisingly difficult. The CEPI entry points out that it's still an open problem.
Yeah, even though the idea has been around for centuries, pinning down a rigorous definition is tricky.
So we intuitively get it, a set of instructions for accomplishing a task, but making that precise is challenging.
Exactly. The term itself comes from the name of a Persian mathematician, Al-Khwarizmi, from way back in the 9th century. And the need for a precise definition, it really came to the forefront during the foundational crisis in mathematics in the early 20th century.
Right, when mathematicians were grappling with the very foundations of their field. Exactly. And that led to the concept of effective calculability, which is basically a procedure that can be done by a human with pen and paper in a finite amount of time without any leaps of genius or intuition.
Okay, so a purely mechanical process, step by step. What were some of the early attempts to define algorithms more formally?
Well, Markov, he described an algorithm as a process that's determined, meaning the next step is always clear, applicable, meaning it works for a whole class of inputs, and effective, meaning it gets you a result in a finite number of steps.
Okay, that's a good start.
Then clean, he added some more requirements, like finiteness, both in the number of instructions and the steps, and mechanical executability, meaning it can be done by a machine without any thinking involved.
Okay, so it has to be a finite mechanical process. What else?
Knuth, in his famous work, he laid out 5 key features of an algorithm: finiteness, definiteness, input, output, and effectiveness.
Okay, break those down for me.
Finiteness, we've already talked about. Definiteness means each step is clear and unambiguous. Input means the algorithm takes some data as input, or maybe none at all.
Zero inputs. What would that look like?
Well, think of an algorithm that generates prime numbers. It doesn't necessarily need any external input. It just starts churning out prime numbers based on its internal logic.
Okay, that makes sense.
Output means the algorithm produces some result, or maybe none, like if it just modifies something internally and then stops. And effectiveness, that means the basic operations have to be simple enough to be done with just pencil and paper, in principle.
Okay, so Knuth really emphasized this idea of a step-by-step process that could be carried out mechanically.
Absolutely. Now, besides these informal definitions, there have also been attempts to define algorithms more formally.
Ah, yes, the allure of formalization.
Right. Kirevich, for example, he argues that maybe we can't have a single universal definition of an algorithm because the very idea of what an algorithm is keeps evolving.
That makes sense. With the rise of parallel computing, quantum computing, the landscape is constantly shifting.
Exactly. But Gurevich, he does propose an axiomatic definition for classical sequential algorithms using a framework called sequential abstract state machines, or ASMs.
Okay, ASMs. What are the core ideas there?
There are 3 main postulates. First, the sequential time postulate, which says that the algorithm works in discrete steps, one state after another. Second, the abstract state postulate, which says those states can be represented as these formal structures. And third, the bounded exploration postulate, which says the algorithm only looks at a finite part of its state at each step.
Okay, so a very step-by-step structured approach.
Right. But Mashravakis, he's not entirely convinced by the ASM approach.
Oh, there's always a dissenter. What's his issue?
He argues that ASMs, they're good at modeling how algorithms are executed, but they don't capture the essence of the algorithm itself, which he sees as more abstract, more mathematical.
Interesting. So for him, the algorithm is more like a pure mathematical function, and the ASM is just one way to implement it.
Right. He uses the example of the merge sort algorithm. You can have many different ASMs that implement merge sort, but the underlying algorithm for Mostowakis is more fundamental.
Okay, I see. So he's emphasizing the distinction between the algorithm itself and its various implementations.
Yeah. And then we have Primero, who comes in with his own take on algorithm definition, proposing 3 levels of abstraction for algorithms.
Okay, Primero loves his low A's.
He does. So at the highest level, you have the informal specification, which is just a general description of what the algorithm does.
Like the big picture view.
Then, at a lower level, you have the procedure itself expressed in some formal language.
Okay, so the actual instructions.
Right. And at the lowest level, you have the implementable abstract machine, which is basically a formal specification of how that program will be executed on a specific machine.
So 3 levels of increasing concreteness.
Exactly. And Primero uses these concepts of simulation and dissimulation to say when 2 machines can be said to be implementing the same algorithm based on their behavior.
Makes sense. You don't know if they're doing the same thing functionally, even if the implementations are different. Now, what about informal approaches to defining algorithms? It seems like despite all these attempts at formalization, there's still value in those intuitive understandings.
Absolutely. Vardy, for instance, he points out that there's still no consensus on a formal definition, and maybe, he suggests, informal definitions are just more useful for everyday conversation.
Right. Sometimes too much formality can obscure the basic idea.
Exactly. Rappaport, he gives a nice summary of those classical informal definitions. An algorithm, he says, it's a finite set of unambiguous statements that an executor, human or machine, can follow in a finite amount of time to achieve a goal.
Okay, clear, concise, gets the point across.
Right. And Hill, he builds on that, giving a more detailed informal definition. He says an algorithm is finite, abstract, effective, has a compound control structure, is imperatively given, accomplishes a purpose, and operates under certain provisions.
Okay, let's unpack that a bit. Imperatively given, does that mean it's like a sequence of commands?
Yeah, it tells the executor what to do step by step. And provisions, those are the conditions that need to be met for the algorithm to work correctly.
Okay, so it has to be given the right kind of input, the right context.
Exactly. Hill also points out that this definition helps distinguish algorithms from things like recipes, which might not always be effective, or games, which aren't always given as strict sequences of steps.
Oh, okay, I see. So algorithms are a very specific kind of procedure with a particular structure and purpose. Now, how do programs fit into this whole picture? The SEP entry says their ontological status is tied to how we view computational systems in general.
Right. If we stick with that software-hardware distinction, programs are often seen as the prime example of software.
Right, they're the abstract instructions that the hardware executes.
Exactly. But if we think in terms of levels of abstraction, programs are situated as the linguistic implementation of algorithms.
Okay, so they sit somewhere between the algorithm and the machine code.
Precisely. Now, the SEP entry goes into 2 main philosophical views of programs. One is programs as theories, which might sound a bit strange at first.
Yeah, how could a program be a theory? Theories are about explaining things, aren't they?
Right. This idea came out of cognitive science from people like Newell and Simon. They propose that programs that simulate human thought processes could be seen as empirical theories of those processes.
So if a program can do what a human can do, maybe it's telling us something about how the human mind works.
Exactly. The idea is that the program's execution, its behavior, might mirror the steps and representations involved in human thought.
Interesting. So the program's like a model of the mind.
Right. And people like Polishin and Johnson-Laird supported this view, arguing that programs are actually really good for building and testing theories of the mind.
Because they force you to be precise, to spell everything out in detail.
Exactly. But not everyone was convinced by this programs as theories idea. Moore, for example, he had some objections.
He always does. What were his concerns?
Well, he argued that programs, at best, they're computational models. They can simulate things, but they don't necessarily explain things in the same way a scientific theory does.
So a program might be able to do what a human can do, but that doesn't mean it's doing it the same way.
Right. And Moore also pointed out that to even interpret a program as being about something real, you need to define these semantic functions that map the program's internal workings to the things in the world they're supposed to represent.
Okay, so you need a way to connect the symbols in the program to the things they're supposed to stand for.
Exactly. And Thagard, he also had some issues with this programs as theories idea.
Another dissenter. What were his points?
He argued that programs don't really fit the traditional views of what a scientific theory is, both in terms of their form and their content.
Okay, so how do theories usually look, according to those traditional views?
Well, one view is the syntactic view, which says theories are basically sets of declarative statements, like axioms. Programs, on the other hand, they're procedural. They're sequences of instructions.
So they have a different kind of structure.
Right. And the other view is the semantic view, which says theories are collections of models that satisfy certain laws. Programs, they might simulate those laws, but they don't necessarily embody them in the same way.
Okay, I see. So Thagard's saying there are fundamental differences between the way programs and theories work.
Right. And he also pointed out that programs often include a lot of implementation details that abstract scientific models usually try to avoid.
So there's a difference in level of detail.
Exactly. But Rappaport, he offered a counter-argument about this distinction between declarative and procedural languages.
Ah, yes. Rappaport, always coming in with the nuances.
He pointed out that this distinction isn't as clear-cut as it might seem. Many procedural languages can be translated into declarative forms, and some languages can even be used in both ways.
Interesting. So maybe the line between declarative and procedural isn't so rigid after all.
Right. And Nair, he had a different take on this whole debate. He believed that programming itself involves theory building, but the programs themselves aren't theories.
Okay, so the process of creating a program might be theory-laden, but the end product is something else.
Exactly. Nair said that good programmers, they need these theories of the program, these understandings of how the program works.
So it's the knowledge in the programmer's head, the shared understanding among the development team. That's the theory.
Precisely. And that knowledge, Nair argued, is more important than any formal documentation or specification.
Because it's the knowledge that guides the creation and evolution of the software.
Exactly. And then we have Turner, who, as you might expect, sees programs through the lens of formal languages and mathematics.
Right. Turner always bringing it back to the formal stuff.
He sees programming languages as mathematical objects, with a formal grammar and semantics. The semantics, the meaning, can be defined in different ways, but in any case, for Turner, programs are essentially mathematical theories.
Okay, so a program is a formal system with a well-defined structure and meaning, which is kind of like a mathematical theory.
Right. So you can see this whole idea of programs as theories, it's a complex and multifaceted issue.
Definitely. Let's move on to the alternative view. Programs as technical artifacts. This connects back to our earlier discussion about computational systems themselves.
Right. Turner is a big proponent of this view. He argues that programs are like other human-made tools, like bridges or cars. They have both functional properties and structural properties.
So the functional properties are what the program is supposed to do,
Mm-hmm.
and the structural properties are how it's built.
Exactly. And the functional level, the meaning of the program, can often be studied as a formal theory.
Okay, so you can have a mathematical theory of what the program is supposed to do.
Right. But the structural level, that's about the concrete implementation, the code itself, and how it runs on the hardware.
So it's about the physical realization of that formal meaning.
Precisely. And a key part of this view is that the semantics of the programming language, the way meaning is defined, has to provide criteria for determining if a program is correct.
Okay, so the language itself has to have a way to say if a program is doing what it's supposed to do.
Right. And the programmer, when they write a program, they're making a claim about that correctness. They're saying this program, when executed, will fulfill the intended function.
So they're not just writing code, they're making a kind of guarantee.
Exactly. Now, one last thing on programs. How do they relate to the world outside the computer?
Right, we've been talking about programs as these abstract things, these formal systems, but ultimately they have to interact with the real world, don't they?
Absolutely. Some people argue that this relationship is mediated by models. So you have a program, which is a model of something, and that something is itself a model of some aspect of the real world.
Okay, so it's models all the way down, or up, I guess.
Right. And this helps to explain how we think about correctness. A program is correct if it's consistent with its specification, and that specification is a model of what the program is supposed to do in the world.
Got it. So the program is a model of a model. Now, Rappaport, he distinguishes between two views of how programs relate to the world.
Yeah, he talks about a wide view and a narrow view. The wide view sees programs as having this direct reference to things and actions in the real world.
Okay, so the program is directly about something out there.
Right. But the narrow view, which Rappaport prefers, sees programs as only referring to the internal operations of the machine.
So it's just about symbol manipulation, not about the external world.
Exactly. Rappaport argues that computation, at its core, doesn't need any external input or output. He uses the example of a Turing machine, which can run on its own without any connection to the outside world.
Right, the Turing machine, that theoretical model of computation.
Yeah.
It's a closed system in a way.
Exactly. And Rappaport also argues against the idea that programs need to be teleological, goal-oriented. He says that for a machine to execute a program, it doesn't need to understand what the program is for, it just needs to follow the rules.
So it's all about the syntax, the rules of symbol manipulation, not the semantics, the meaning.
Precisely. Now, this raises an interesting question. If computation is just symbol manipulation, how do we even say that two programs are the same program if they don't have the same external effects?
Right. How do you determine identity without reference to the outside world?
Piccini, he proposes this idea of internal semantics, where the identity of a program is determined by its internal structure, its syntax, and the operations it performs.
Okay, so it's about the internal logic, the way the symbols are manipulated.
Right. But Spravak, he gives a counterexample. Imagine two programs for addition, one using Arabic numerals, the other using Roman numerals.
Okay, I see where he's going with this.
Internally, they look very different, but they're doing it.